Alright, hi guys, I'm Daniel Carter. I'm the president of Juggling Club, and I'm a junior math major here. And I learned how to juggle because of like some stuff I did in high school, like some math research experience involving juggling. And so then I learned how to juggle, and then I like juggling a lot. So, okay, so yeah, so okay, what is juggling? Well, juggling is like three things. First, it's a performance art. So maybe you've seen Juggling Club perform, do filler acts for other shows. We do that a lot. It's also a sport. Like a lot of people do it for exercise, or there are like juggling competitions and so on. But it's also a science, which is very strange. And I'm going to talk about exactly like some of the scientific and mathematical aspects of juggling. And really, these things are interconnected. So a lot of times, people will be researching something, and they'll discover a new juggling pattern, and then the sport people will like learn how to perform it, and then eventually they'll get used in performances, which is a neat sort of thing. All right, so we'll start with physics. The first thing to consider is just one throw, and exactly what's going on here. Well, there's sort of two parts of this throw. There's the actual throw itself, where the ball is airborne, and it has some flight time, and then there's the part where you're holding the ball and it has some dwell time. So if I take a juggling pattern here, you can see one of these balls is just exactly the same as that single throw. So you're just doing this 3 times as fast. And so each ball is following the same path, and they have the same throw time and same dwell time. But you can think about this from another perspective, which is instead of considering what the ball is doing, you can consider what your hands are doing. So this is from the perspective of a ball. If we look at it from the perspective of a hand, then a hand is either vacant or it's holding a ball. So we have a different quantity here, the vacancy time, and also the same dwell time as the ball has. But you can think about this, and you should think about like the total time in looking at a juggling pattern from both of these perspectives should be the same. We should be able to equate these in some way, and indeed this is possible. So if you take the flight time and dwell time and divide it by the number of balls, this is equal to the vacancy time plus dwell time divided by the number of hands. And this is it's called Shannon's theorem, named after the father of information theory, Claude Shannon. A picture of him juggling. And so really what this is saying is that at each point in time, each ball is either in flight or it's being held, and each hand is either not holding the ball or holding the ball. Is really what that's saying. And we can rearrange this equation, just cross multiply, and get this, and this is sometimes uncertain. And this quantity, flight time plus dwell time times the number of hands, or vacancy time plus dwell time times the number of balls, is actually equal to the period of the pattern, like in seconds. So this allows you to, if you know some of these quantities, you can calculate the other ones fairly easily. And flight time in particular is interesting because it's just projectile motion. This is like really basic physics. We can calculate it in terms of height and exit velocity. So we know that in the sort of as the ball travels, it goes from having a positive v velocity to negative v velocity when you catch it. So that means that the change in velocity, which is 2v, has to equal the gravitational acceleration times the flight time. And also, due to conservation of energy, we know how high it's going to go based on the exit velocity. And so we can rearrange this and solve for flight time in terms of height. So this is telling you, if you want a particular flight time, how high should you throw it, or vice versa. And the constant isn't so important. Really, the important relationship is that the flight time is proportional to the square root of height. But by Shannon's theorem on the previous slide, we know that the sum of flight time and dwell time scales linearly with balls. It's proportional to the number of balls. And the dwell time is like pretty negligible compared to the flight time. If you are juggling like 5 balls, say, each ball is staying in the air. Each ball is staying in the air a lot more than it's in your hand. So flight time is really the vast majority of the time. And so we can conclude that if you're throwing it at like a constant tempo, and you're not sort of varying it, then the height that you're throwing the balls to should be roughly quadratic in the number of balls you're juggling. So if I juggle 3 balls, it's very low down here. If I try and juggle at the same speed, 4 balls, it's much higher. And then 5 balls at the same tempo is really hard to do because well, you have to throw them very, very high. I mean, my skill tops out at 5 balls, but there's simulation programs you can use to simulate any number of balls. Here I have 3 through 7, and you can see as the number of balls increases, the height increases very quickly. And here I've set it so that the dwell time is exactly the same between all of them, and the tempo is exactly the same. So you see this nice quadratic curve. Of course, jugglers don't actually throw balls this high for 7 balls, or even this high for 5 balls. So what actually happens is a little bit more complicated. There's a pretty interesting video by a juggler named Ehernborg. I'm not sure if I'm pronouncing it correctly, but and he took a video of himself juggling 3 through 9 balls for a minute each and timed it. And it's really actually quite complicated. So the number of catches per second doesn't stay constant, it actually increases, but it increases non-linearly with balls. And this is basically because there's an upper limit to human strength. You can only throw so fast or throw so high. And so the graph of catches per second, as you increase the number of balls, something like this. And you can calculate out using Shannon's theorem what that should mean for the height of your throws, and it looks like this. You know, it increases at an increasing rate, but it's not exactly a quadratic function, or even approximately a quadratic function. Also, there's like some weird things that happen. So even number of balls end up being thrown slightly slower than expected, and I can demonstrate why that's the case. So for odd balls, each ball gets thrown to the opposite hand. So my right hand throws to my left hand, and vice versa. But for an even number of balls, the throws are to the same hand. So all the balls that I'm throwing with my right hand stay in my right hand. So it's really just juggling 2 balls in one hand each. And because of that, the sort of exact mechanics of how you're throwing it changes, and it turns out for even numbers, it ends up being a little bit slower. And also, it's really dependent on the juggler. So different people juggle slightly differently, and this can have some pretty big effects on exactly the height they throw to and so on. And for club juggling, it's even more complicated because now you have to take into consideration the rotation of the club, because you're not, you can't just throw it however. You have to catch it at a particular point in its rotation. And that turns out to be sort of the dominant factor. It's not the number of clubs, it's really the number of rotations that's important for club juggling. So the natural number of rotations is, if you have n balls, is to do n over 2 rotations. And it seems to me that the angular velocity that you throw them at is constant. And so this means that the height that you throw them to is like this weird stair shape, and it's also linear. If I can demonstrate some of that. So if I am doing 3 clubs in singles, so just doing a single rotation, it's way down here. Then if I do double rotations, I have to throw them a lot higher. And this is like the height you have to throw them at if you're juggling 5 clubs, so approximately. So here's like an excerpt from this video by this guy where he's showing this is 6 clubs versus 7 clubs, and then we'll see 8 versus 9. And you can see they look, it's like the same exact height basically. And here's 8 versus 9. Again, like almost exactly the same height, just because they have the same number of rotations. Okay, that's enough physics. I'm not traditional. Let's talk about math. So this is all fine and dandy for like basic patterns, but there's like a lot more than just the basic pattern, right? You can do crazy things where you're holding onto a ball for a really long time and holding a ball in 2 hands, or juggling 2 balls in 1 hand and then switching back to the normal pattern, and like throwing behind the back and all that sort of stuff. And this, you can analyze each of them, but we'd like a sort of general theory of this. And so, yeah, so the basic pattern is called cascade for an odd number of balls, or fountain for an even number of balls. There's other patterns. So there are a couple, like there's the W for the pattern, and there's shower is this, snake is like this, columns, there's box, and half box. How is this? And there's more patterns. Waterfall. This one in a while. Like this. There's weave. This, and there's windmill, and nose mess, and Brooks Garage. Anyway, and so on and so on. There's hundreds and hundreds and hundreds of juggling patterns. So how do we analyze them? Well, one way to do it is to draw the trajectory of each ball 3 times in a sort of abstract way. So we're going to have a time axis going up, and we're going to denote basically which balls are in each hand at each point in time. And so the basic cascade pattern looks something like this. So you throw a ball from the right hand, and then you catch it in your left hand 3 beats later. You throw a ball from your left hand and catch it in your right hand 3 beats later, and so on. Shower, which is this one. The balls coming from your left hand are caught immediately, and the balls coming from your right hand are caught 5 beats later. And then this half box pattern is something a bit more complicated, and now we have throws from one hand to the same hand, and so on. And so what we can do now is we can label these throws. So I said, you throw it and then you catch it 3 beats later. So let's call that throw a 3. And then here, let's call this throw a 1 because you catch it 1 beat later. And this throw, you catch it 5 beats later, so it's called a 5. And so on. And so for the cascade of 3s, for shower, it alternates 5, 1, 5, 1. For half box, it turns out to be 4, 4, 1, 4, 4, 1, 4, 4, 1, and so on. And so, well, now we can replace these names with sort of a systematic naming scheme based on these numbers. We just take the repeating unit, and that's going to be the name of a juggling pattern. So cascade is called 3, and shower is called 5, 1, and half box is called 4, 4, 1. Actually, half box is pretty interesting because 4, 4, 1 is the normal name for half box. Half box is sort of the alternate name that people came up with afterwards. That's because this pattern was actually discovered based on this notation. People were drawing these ladder diagrams, and they found this repeating pattern, and then they learned how to juggle it, but they didn't have a name for it, so they just called it 4, 4, 1. And so these numbers are essentially telling you it tells you the time, which is is proportional to the square root of the height of each throw. And so, and also there's some special cases. So for low numbers, sort of sometimes you don't even throw it. So a 2 just means you hold onto the ball. So if you think about what a 2 would mean, you'd throw it, and then your other hand does something, and then you catch it immediately in the same hand. So you might as well have just not thrown it at all. So 2 is realized as just holding onto the ball. So the W pattern is 4, 2, 3, 4, 2, 3, 4, 2, 3, 4, 2, 3, so on. A 1, as we saw, is a quick pass between hands. So this is just doing 1, 1, 1, 1, 1, or 5, 1, 5, 1, 5, 1, 5, 1. A 0 means that there's not a ball in your hand, and it's just a beat passes and there's no ball in your hand. So, example of snake, 5, 5, 0, 5, 0. This one's really hard to count up, but you can see that my hands are empty a lot, and those empty beats are correspond to the zeros. And we can continue this. The -1 would be throwing a ball back in time and catching it on the previous beat. Jugglers are still working on how to do that. And alternatively, so if you actually draw out the ladder diagram for a -1 throw, right, it looks something like this. and then maybe throw it up here, and we start from down here. We can think about this as like a Feynman diagram. And so what's actually happening here is that at the previous beat, we produced a ball and an anti-ball. We threw the anti-ball forward, and now we're at this beat, the -1 beat, we're catching an anti-ball and annihilating it with a matter ball. I don't know. Ask Stern about it, I guess, if you want to juggle with -1. Okay, so anyway. So how do we generate juggling patterns? Well, you can draw ladder diagrams and you can sort of figure out that way, but we like to work basically with just the numbers, ideally, to make it easier on ourselves. So turns out at each beat, the only information that we need to know sort of what throws are legal and which ones aren't legal, is when each ball currently in the air is going to land. So here's an example. So it's possible, for example, that this red ball is in your hand currently, and the blue ball is going to land in your hand on the next beat, or it's going to land on your other hand on the next beat, and then the green ball is somewhere higher up in the air and it's going to land in 3 beats. And then maybe I throw the red ball to height 5, so that means it's going to land in 5 beats, and so it goes up here, and all the other ones, since we're 1 beat later, have fallen down by 1 beat. And then maybe I throw a 1 with the blue ball, and it, I throw it up 1 and then it immediately falls down, so it stays in the same place, which means that I throw and catch it immediately, and all the other balls fall down. And we notice that this state is the same as this state, so it means that 5-1 is a valid juggling pattern, as we saw. Let's see, this would be this with the right colors. And so we call this string. You put a 1 if there's a ball there, and a 0 if there's sort of a gap in that time step. No, it's the same. So this would be 1 1 0 1 0 and 1 0 1 0 1. And there's sort of an infinite string of zeros going up to infinity, if you want to think about it that way. And it's called a state. And so the way to generate all juggling patterns is to draw all possible states and all possible transitions between them, like sort of all possible throws. And you do this sort of for a number of balls and a sort of fixed maximum throw height, because obviously you can just throw them as high as you want, and you can get this sort of infinitely large diagram. But for a fixed number, you get a diagram that looks something like this. So this is 3 balls with a maximum height of 5. And so our 5-1 pattern is this cycle up here, and then like this cycle right here, just doing 3 3 3 3. That's the regular cascade pattern. And those other cycles, so for example, 4-2 is this pattern, and so on. And so the way to generate any juggling pattern is to draw this diagram and then walk along the arrows until you end up backward inserted. And so this notation is called site swap. These numbers are called site swap. So some site swaps, if we look at this diagram, we can just sort of get a computer to read off all the site swaps, all the different cycles. And so the sequence sort of begins 3, and then we have 3 of them of length 2, one of which is just repeating 3 twice. We have 6 of length 3, we have 14 of length 4, and then we get 27 and 55, and so on. And so the natural question, which is how many patterns are there with E balls, max height H, and length P? Well, some of these patterns are kind of dumb. Like, okay, 3 3, the pattern 3 3 is just this, which is identical to 3, right? You can't tell them apart if you're juggling them. So we should sort of eliminate some of these patterns which are just repeating the same thing multiple times. So let's call these reduced patterns. So I've crossed them out here. And so this is a sort of more interesting, more natural question than the first one. But so, we still have some problems. So some of these patterns like 4 2 3 is really just doing 2 patterns, right? You're doing 4 2, then you do a 3, and then you're doing 4 2 and a 3, right? So it's sort of composed of smaller patterns, and so some of these patterns are so-called prime patterns, which can't be decomposed this way. So I've crossed out all the composite patterns, and so another question is like, how many prime patterns are there? And what we see is that the vast majority of patterns are composite. Like, we have only one prime pattern, then 2, and then 4, and then, I don't know, but then it drops down from 26 to 7, then 47 to 3, and actually it peters out entirely. There's only 2 prime patterns of length 7 and 1 of length 8, and none of length 9 or more. I'll talk about I'll talk about prime patterns a little bit more later, but for now, let's consider the reduced pattern case, because actually, it turns out that this problem is really, really hard, but reduced patterns is a little bit easier. So let's talk about this, and we're actually gonna not consider our max height. We're just gonna let it go unbounded, and we'll see why we can do that shortly. So one potential way of answering this question is to answer the other question: when is the string of numbers a valid siteswap? And maybe if this has a particularly simple answer, we can just sort of count the number of strings that have this property. So one sort of necessary condition is that the average value of the numbers in a valid siteswap has to be an integer. In particular, it's the number of balls. So if we go back to here, you can actually all these numbers. If you average all the numbers here, you're always going to end up with 3. And so why is that the case? It's actually pretty simple. So let's say we have a state, and this is like a binary string s1, s2, and so on up to the maximum height. Let's define the total height of the state to be the sum, basically, of the indices where the 1s are. And this is more or less like some notion of how much potential energy is there in the system. And so after I do a throw of height m, the total height of the state changes by m minus b. So it increases by m because I threw height m. Then it decreases by b because every ball fell down by 1. But in a juggling pattern, they return to the same state after some number of throws. So if we sort of add up all of these changes and then divide by n, we should end up with an integer, which is going to be exactly b. And that's the truth. Unfortunately, there are sequences that have an integer average which aren't valid. For example, something like 3, 2, 1 would not be valid because if I look at a ladder diagram, if I throw a 3 here, this ball would land here, and then I throw a 2, and then I throw a 1, well, all 3 balls are going to land on the same hand at the same time, which is a problem because you can't continue juggling in that case. So this is a necessary condition, but it's not sufficient. So let's return. So here's the full characterization. This was discovered used for Buhler, Eisenbud, Graham, and White. This is David Eisenbud, Ron Graham, and Colin White, are relatively well-known mathematicians, I think. I managed to find pictures of 3 of them juggling. I couldn't find a picture of Eisenbud juggling, unfortunately. Well, okay. So the characterization is that a sequence of integers is a valid siteswap if you add the index to the value and take it mod n, if that's a permutation of the natural numbers, and all those numbers are distinct, basically. And so I'm not going to go over the proof of this. It's relatively straightforward, but the main ideas are that if you add or subtract n from any number in a valid siteswap, you get another valid siteswap, just with more or fewer balls. So if you take, say, 5, 1, that has n equals 2, and I add 2 to the 1, I get 5, 3, and that's this 4-ball pattern. And then also this value at plus t. Well, t is when I'm throwing a particular ball, and at is when it's next going to land. So at plus t is the time that a ball thrown at time t will land. And so in order to avoid collisions, those all have to be distinct, which is exactly this condition that these numbers mod n are a permutation of the natural numbers. And so this characterization is not the greatest. You can do the work and find the answer to this question: how many reduced patterns are there? But the work is fairly complicated. The original proof that they found used like some combinatorial identities using Eulerian numbers, which are counting permutations with a certain number of like rises. So how many times is the next number in a permutation greater than the previous one? And it's not exactly trivial. And there's other problems like you need to account for a cycling pattern to start at a different place. So the pattern 5-1 is the same as 1-5, just starting from a different place within the cycle. You also need to end up with the right number of balls. So, like I said, when you add or subtract n, or when you do this modulo operation, you're adding or subtracting numbers of balls, which is a problem because we're trying to keep the number of balls to a fixed number. And well, if you do the work, then you get this somewhat complicated formula, which is number of reduced patterns is 1 over n times the sum of divisors of the Mobius function evaluated at n over d times its value b minus 1 or b plus 1 to the d minus b to the d. And if you're not familiar with it, is this Mobius function, which is encoding some information about the prime factorization of n. So the proof is somewhat complicated. Later, a simpler proof was developed, which I will present to you. So what we're going to do is we're going to draw a ladder diagram, but only with one hand. So siteswap doesn't know that we have 2 hands. So what we do is we just have one side. So for example, like the pattern 3 would just be this sort of repeating pattern. And then we're going to distort these curves in some way. And I'll describe exactly how to do this. And then it turns out that we can sort of cut this pattern at each throw and end up with sort of standardized, so-called juggling cards. It turns out that if you arrange these juggling cards in any way, you always end up with a juggling pattern. So here's a more complicated example. So this is the pattern 4-2-3 as a one-handed ladder diagram. And so the first step in this distortion is that we're going to move the peak of each curve directly over where it lands, and then we're going to attach that peak to the throw with a straight line, and attach the peak to the catch with also a straight line. So for this pattern, this looks like this. The next thing we're going to do is we're going to shorten all the peaks as much as possible. So for example, here we're going to move this down by 1 unit basically. In order to make the lines match up, we're going to bend this line down so it looks like a V. So if we do that everywhere, we get this. And now we can cut it up into these juggling cards. And so if you just look at one card, basically it's describing some of the balls are moving up, and one ball is falling all the way down and being caught. And you can see for this pattern, there's 2 juggling cards that show up. So there's this one where the top ball falls all the way down, and there's this one where the second ball falls all the way down. And not pictured are, there's 2 more juggling cards. One of them has the first ball fall down, and then one of them has none of them. So that juggling card is like just looks like this. And this would correspond with 0 in siteswap. So anyway, for a number of balls, there are a total of b plus 1 cards you can end up with. And so I said that any arrangement of them is going to give you a ladder diagram, sort of. And so there's b plus 1 to the n. Arrangements of n of them, if you repeat those, that'll give you juggling patterns, almost. Except there's some problems you can end up with. So if we take one of these, which where the top ball doesn't fall all the way down, then we just have this ball that's just floating up there the whole time, which is a problem. So this is not a ladder diagram, but it turns out if we just ignore all of the balls that never fall down all the way, or are never thrown and caught, then we do get a ladder diagram just for a smaller number of balls. So this corresponds to the ladder diagram for the pattern 2, which is very boring. Just this. But it's a juggling pattern nonetheless. So that means that any arrangement corresponds to a ladder diagram with not b balls, but at most b balls. B balls are fewer. That's really nice because that means if we just subtract the b minus 1 case, we have the number of patterns with at most b balls minus the number with at most b minus 1 balls, which is just exactly the number with b balls that we want. So this gives us b plus 1 to the n minus b to the n. We're not done yet, because this is counting cyclic permutations of the same pattern as being distinct. It's also counting, this is not counting reduced patterns, so I can repeat the same thing multiple times, and I won't be able to tell if that's not reduced. So the way to fix this is to note that for any pattern, or for any so this is basically the number of strings of numbers which correspond to valid siteswaps, but not the number of reduced patterns. But if I have a pattern like 5, 1, 5, 1, like one of these strings, what I can do is I can just look at the reduced section, and all of these sort of, you can split them up into identical sections in some way. And this I know is going to be a reduced pattern, but it could be that it's a reduced pattern, but it's sort of cyclically permuted. And so that means that for each, so let's say our max, or let's say our period is n. That means that we can have the way to form any pattern is to take any reduced siteswap for a divisor of n, repeat it n over d times, and then cyclically permute. And there are a total of d possible cyclic permutations. And so that means that we have this formula that b plus 1 to the n minus b to the n is equal to the sum over divisors of d times the number of reduced patterns of d. And then, well, there's a nice trick in combinatorics called Mobius inversion, which lets us solve for r in terms of the left-hand side. And so if you do that, you get exactly this. Now this is where the Mobius function is coming from. It just comes from this Mobius inversion step. Right. Yeah, so that's reduced patterns. What about prime patterns? So if we look at the juggling diagram again, a prime pattern is a cycle in a graph theory. So that means we can't repeat vertices except at the endpoints. So like 3 is a prime pattern because it only has one vertex, and 4, 2 is a prime pattern because it just uses each one of these vertices once. But 4, 2, 3 is not a prime pattern because it repeats the state. Or something like 4, 5, 1, 2 is not a prime pattern because it repeats the state. Okay, and this explains why why there are finitely many prime patterns for a particular max throw height. And this explains why, for this particular example, the largest one is 8. It's just because the largest cycle in this graph is like 8. And it's actually these middle 8 states, 5, 5, 1, 5, 0, 5, 3, 0. It's a very boring pattern. It's really ugly, unfortunately. Okay, so this problem is really, really hard. Counting the prime patterns is very hard. This graph is like really complicated. There are some patterns which we'll exploit, but really, I mean, this is just flowing so far from there. There are some trivial results. So, for example, for one ball, there's just one pattern. It's in and then a bunch of zeros. We also have the trivial upper bound that, well, the number of prime patterns must be smaller than the number of reduced patterns, and the number of reduced patterns is roughly this. It's b plus 1 to the n minus b to the n over n. So that means that we have at least an exponential upper bound. And there's like one really strong paper on this subject, and they figured out the 2-ball case pretty much exactly. So it turns out for 2 balls, it's asymptotically equal to some constant times 2 to the n, and they have this expression for the constant. It's very complicated. And this is just for the 2-ball case. So 3 balls presumably would have some similar result, but much more complicated still. And they also found a lower bound for more than 2 balls, which is that it's b to the n minus 1 at least. As this gives an exponential lower bound, but it's a different exponential than the upper bound. So there's there's a big gap between them. At least we know the answer is exponential of some kind. In my opinion, a more interesting question is what's the longest prime pattern? This is easier to study. So we have a trivial upper bound, which is just h choose b, because that's the total number of states in the graph. And we also know if there's one ball, or if h minus b is equal to 1, so this is like there's 1, 0 in our states, then the longest prime pattern is exactly h, and it's just the pattern that we saw before, essentially. So we're going to show the following upper bound. The length of the longest prime pattern is h choose b, and we have these two correction terms, minus c of hb. It's the number of two colored necklaces with, I guess, h total beads, k of which are ones, I guess. We'll see where that comes from. And then, so a necklace is a string if you consider cyclic permutations to be equivalent. And then we have this other correction term. If h is exactly 2b, and that's also greater than or equal to 6, then we can subtract an extra 1. That's it. And this is essentially the best known result. And so this first term is due to Waldman, and the second term is due to Discrete Mathematics. So here's how to do it. So if you take the juggling graph, and we partition it into cycles, and within each cycle, we want the only all the throws to be either max height or 0. So for this juggling diagram, it has these two shift cycles, is what they're called. So this first one we have 5, and then 0, 5, 5, 0, and this one we have 0, 0, 0, 5, 5, 5. It's easy to see that this partition exists and it's unique. At each state, if a state starts with 1, then you can do a max height throw from it. Or if it starts with 0, then you can do a 0 height throw. Actually, you can only do a 0 height throw from it. The key observation is that if you're considering some juggling pattern and it goes through a lot of shift cycles, every time you move between shift cycles, you have to use a throw which is neither a max throw nor a 0 throw. It's sort of by definition. But that means that any so-called exit state has to begin with a 1. In other words, there has to be a ball in our hand. If there's not a ball in our hand, then we're forced to make a 0 throw, and we need to make a non-0 throw. So any exit state must begin with a 1, but also any entry state. So the very next state has to end with a 0, because we just didn't do a max height throw. The only way to end up with a 1 in the furthest rightmost position is to do a maximum height throw, just by definition. For example, in this 8 ball, or in this 8 period cycle, we're traveling between both shift cycles. So, for example, this exit state begins with 1, and then this entry state ends in a 0, and this starts with a 1, and this one ends in a 0. And this is nice because if we look at an entry state, for example, this one, and then we look at the state before it in the shift cycle, so we take an arrow backwards, then we know, because this ends in a 0, that this has to start in a 0. Because if it ended in a 1, then that means that the previous one we did max height throw. There's a problem because we know that for state starting with 0, we're forced to make a 0 throw. That means that if we entered the cycle from this location, there's no way we could possibly end up with this state in our juggling pattern without having to repeat this state. And so that means that as long as we go between 2 shift cycles, in every single shift cycle we have to miss at least 1 state. And this is exactly, well, you should say h choose b minus c of h b. And c of h b is just counting the number of these shift cycles, because if you do a maximum height throw or a 0 height throw, you're just actually cyclically rotating the state. This is just counting the number of shift cycles. as long as there's at least 2. And then the extra improvement term, there's, in that case, there's a special shift cycle with exactly two states, which are 10, 10, 10, 10, and 0, 1, 0, 1, 0, 1. And in this case, the first state has to be both the entry and the exit state. And if you consider very carefully what throws could lead you to the state and what throws you can do from the state, you come up with the following. One of the following statements has to be true. Either the previous shift cycle and the next shift cycle are the same, or in the previous shift cycle, the exit state began with 1, 1, or in the next shift cycle, the entry state ends in 0, 0. And in all three of these cases, we have to miss an additional state. And so this shift cycle we can avoid entirely and we miss both states instead of just one. Or if we enter it, we have to miss an additional state in some way. And so the reason you miss an additional state in the first case is because if we enter a shift cycle at 2 different points, both of the previous states in that shift cycle from those 2 points have to be missed. And in the third case, in the next shift cycle, if the entry state ends in 0, 0, then not just the previous state, but the one before that also begins with 0. It's just a cyclic rotation, and so we have to miss both of those. And something similar for the second case. And this is basically all that's known about this problem, as far as I can tell. And of course, there's computational results. We know that this is not equal. It's pretty close, but we know of examples where it's not exactly correct. And there's sort of one last thing to say about this. It's combinatorial with siteswap, which is that anything we can say about the case with height h and b balls is also has some variant or some version that's sort of exactly the same in the h minus b case. This is due to some duality between these cases, which I like to call the charge parity time symmetry. So what we do is we list out all the states reached by a particular pattern, and then we switch 1s and 0s. This is corresponding basically to switching charge. And then we mirror the states, which is like switching parity. So mirror states left to right. We also reverse the order, which is like switching time. And this will give us another valid juggling pattern, but now with h minus b balls instead of b balls. So here's an example. So this is a 3-ball pattern, 4, 5, 3, 0. And we'll turn it into the 2-ball pattern, 2, 0, 1, 5. So first out, we list all the states that are reached by the first pattern. And then we switch all the 1s and 0s. And then we mirror them. And then we reverse the order. And these are the states reached by 2, 0, 1, 5. This is not too hard to prove. And this is sort of the basics of siteswap. There's other extensions. So there's such a thing called multiplexing, which is throwing or catching multiple balls in the same hand. So this is like the basic multiplexing pattern. And so you see I'm throwing 2 balls at once. And it's called, we use these brackets to denote the height where each ball is thrown. So here, what you do, to figure out that I have 5 balls, you add the numbers, and 3 plus 2 plus 5. So I'm throwing 1 ball to height 3, I'm throwing 1 ball to height 2. Although I said that 2s are hold, so this is, 3, 2 is actually this pattern. I'm just holding on to 2 extra balls. If I want the throwing them as well, then I can denote that with a T. And that's just sort of just a notational check. These patterns are similar. There are other things. So this is just, so far we've talked about asynchronous patterns. So synchronous patterns, especially for even numbers of balls. So this 4, 4 pattern is this pattern. So compare this to the asynchronous 4-ball pattern. The only difference is that I'm throwing the balls at the same time. But also I can throw the balls to the other hand, so it's the same rhythm, just changing where I'm throwing the balls. It's called 4x4x. and there's passing. So here, each number has a left side and a right side, and this is describing what the first juggler is doing and the second juggler. This P means the passing between them. This is just sort of the basic passing pattern. You have 6 balls total, and you have 2 people in the passing between them. And also, one might want to consider different balls distinct. So maybe instead of having our state be a binary string of 1s and 0s, we have 0s, but then we have like A, B, C, D for different balls, or different colors or whatever. So maybe we want this pattern to be different than if I swap these 2 balls to this pattern. And they're different in the sense that in this pattern, my right hand is throwing blue, red, green, blue, red, green, but then here it's throwing, it's throwing blue, green, red, blue, green, red. So maybe you want to consider those distinct. For like a more dramatic example, here the 3 objects you're juggling are really different, like a bowling ball, an apple, and an egg. This is very important. You can eat the apple, this one, but anyway, yeah, that's enough contrast. Let's talk about policy. Okay, so let's talk about more complicated juggling again. Siteswap is not perfect. It describes a lot of patterns, but the problem is that it doesn't differentiate between some patterns that are different. So for example, the basic cascade pattern has siteswap 3, and this pattern, mess, also has siteswap 3. If you keep track of what hand is catching and throwing which ball, it's exactly the same between 2 patterns, but clearly they're very different. And you can come up with, endless extensions of siteswap to notate different things like throwing under arms and throwing under legs and behind the back or whatever. So here's some examples. So cascade, outside throws, windmill, nose mess. These are all the same pattern in terms of siteswap. And there's another thing that can happen. So siteswap, as I mentioned, doesn't know that we have 2 hands. So this pattern 5-1, which is a right-handed shower, maybe you want to consider it different from 1-5, which is a left-handed shower, which I'm not very good at. And in my mind, the bigger problem is that siteswap does differentiate patterns which are actually the same. So here's an example. So 3, 5, 2, 2, and 7, 2, 2, 2, 7, 2, 2, 2, 2. These are all really the same pattern. So here's what 3, 3, 3, 3, 3 looks like, and then 5, 2, 2, 5, 2, 2, 5, 2, 2, 5, 2, 2, 5, 2, 2. But it's just the same pattern, right? I'm just throwing it slower, really. And then 7, I'm throwing it even slower. So probably want to consider these the same pattern. So I'm just changing the rhythm here. I'm not changing sort of the essence of the pattern. So here's an idea on how to fix these, how to annotate them. If we attach a string to each ball and we juggle them, then we end up making a braid. And also
for example,
notates body information.
But also, you can start to see the relationship of my body to the object. If I start to try to unwind the string on purpose, and in this way we have a record of where all these objects have been the entire time they've been manipulated. Here's that pattern again. I showed you at the beginning.
That's pretty impressive. You managed to keep on juggling for so long because it took a lot of resistance. But anyway, so that's the idea. And so this is, so like I said, if we ignore the body for now, the juggler's body, leaving it behind the back and so on. If we just consider the balls of yarn, that is gonna make a braid as we start juggling. And well, there's a branch of math called braid theory, or knot theory, which is allows you to analyze this. And the basic idea here is that ladder diagrams are going to give you braid diagrams and vice versa. So here's an example. So we have the ladder diagram for cascade, except I put it on the side, and here's a braid diagram just representing a particular mathematical braid. Well, in general, the juggling patterns are going to be infinitely long in either directions if we think about just repeating it forever. But we can just take a finite chunk of it. That's going to give us a braid. Computer a finite braid. And so there's this theorem by Devadoss and Mugno that any braid can be juggled. And so the idea behind this is that, well, we can make the trivial braid, and what we do is we throw both exponentially high. So let's demonstrate with this diagram. So the first ball we're just throwing, whatever speed we're throwing it at, and the second ball we're throwing it 9 times slower. And so this, the effect of this is that it ends up always being above the first ball that we're throwing. It's just always higher, even when we're catching it. And then we throw the third ball 9 times higher still. And so this means that basically none of the balls are interacting with each other in a topological sense. And so we get a trivial braid, where all the strands are just distinct from, or completely disjoint from each other. And then we can make other braids just by varying when exactly we're catching the balls and exchanging them. So we turn the ball at the lowest level to the second level and we switch them. This is going to introduce a crossing, either an overcrossing or undercrossing, depending on what we want to do. So here's an example. So we have this red ball is being thrown higher than the black ball, and if we just catch it at a slightly different time and then switch it, so this diagram continues with the red ball being lower and then the black ball being higher. We'll introduce a crossing there. It's specifically undercrossing. So then here we do a similar thing the other way around and get an overcrossing. And using these sort of building blocks, you can build up any braid. And the last thing is knot theory. So if you take a braid and you imagine joining the ends together, this is going to give you a knot. So here's an example. We had a piece of the 3-ball cascade braid, and if we join the ends together and manipulate it a little bit, it turns out that it's this knot, and this knot is the figure 8 knot, or the knot with 4 crossings. Although here not shown with 4 crossings. And so we can juggle all braids, and Alexander's theorem, very famous, is that any link or knot that you come up with as a closed braid. So you can always turn a knot into a braid, and then from the previous theorem, you can turn a braid into a juggling pattern. So this means that all knots can be juggled, which is great news for now. But so let's so did we fix the problems with siteswap by considering this sort of topological thing? No, not really. So knot theory still doesn't differentiate patterns that are different. So for example, windmill and shower. Alright, so windmill is this pattern, and shower is this pattern, and the ball is moving exactly the same way. My hands are doing something different. So these are different patterns. But topology, if we only consider the balls, we'll say these are the same. If we do sort of the full thing from the TEDx talk, and we include our body parts along in this topological model, then we can differentiate between these. Because in a windmill, I'm doing some under the arm throws, and so that's going to loop around. The balls are going to also loop around my right arm. But even including body parts, there are some patterns we can't differentiate. For example, there's this pattern Boston mess, which is like this. And I can't differentiate this from columns, which is this. And this is because although my arms are moving left and right, it's actually not, they're not interacting with the balls at all. They're just sort of moving back and forth like this, always underneath the balls. So I can't differentiate between these two patterns. And also, even more certainly. So in both of these examples, siteswap does differentiate between these. These are sort of new problems, but there are actually multiple types of Boston mess. So there's like this, where my left arm is always over my right arm. But then there's this version, where my right is always over my left. These are different, but both siteswap and topology would say they're the same. And well, the bigger problem is that, okay, so knot theory does solve the problem. If you get two different knots from two different patterns, you do know that they're different patterns. That is true. But the bigger problem is that knot theory is really hard, and telling whether two knots are the same or different is like really, really, really hard. It's computationally difficult. It's theoretically difficult. So, you know, we've solved some problems, but at what cost? And basically, the moral of the story is that all models are useful, or all models are incorrect. Some models are useful. Knot theory turns out to not be a very useful model, although it's more correct than siteswap. If you ask any professional juggler, they're going to know what siteswap is. They're going to know how to read siteswap and be able to do various siteswaps. They're not going to know anything about knot theory. Yeah, thanks. That's the talk. Hope you enjoyed.